Hello and welcome to Carl and Cymru. My name's Mr. Black and I teach at Penglau School in Aberystwyth. I'm going to be going over some Year 10 content with you today in this presentation, and we're looking at rates of reaction. Okay, so these the syllabus, so the kind of content you need to be aware of. The subjects E and F on enzymes is for triple award students only, so I won't be going over that content today. So yeah, we're going to break the unit down into a series of pieces. So the first piece I'm going to look at is about what is rate of reaction. So rate of reaction is literally how fast reaction occurs, and specifically we're looking at how quickly something gets used up, i.e. reactant gets used up in a reaction, or how quickly a product gets formed. Both are good. Typically at GCSE we're going to be looking at how quickly a product gets formed. So for example, you can see this is a reaction between some magnesium mesylene acid, and for example we'd be looking at how quickly the gas forms in this reaction. And we'll look at some ways in which we can actually measure how quick the gas is forming. Or we could, time how long it would take for the reactant, the magnesium, to actually fully dissolve. But yeah, typically we'd probably be looking at how quick the gas forms. So what we're going to be doing then is one of the areas we're going to look at first of all is the things that affect rate of reaction, i.e. the factors. And then we're going to explain why they affect rate by using something called collision theory. Okay, so what does collision theory state? Well, collision theory is the way that we can explain why the following factors affect rate of reaction. And what are those factors? Well, one of them is temperature. One of them is concentration. One of them is surface area. And one of them is the addition of a catalyst. And hopefully you know how these things affect rate. And I'll go over that with you now, and also why. So why do they affect rate? Well, it's all to do with this idea of collision theory. So we'll start with what collision theory is. So collision theory just literally states that for a reaction to take place, particles have to collide. Once they've collided, the energy that's released in that collision will break their bonds so that they can reform their new products. Okay, so you can see here we've got two particles, reactant A and reactant B. When they collide, there's energy released in that collision, and now you can see that those particles have been able to break apart from that energy being released, and then that allows them to recombine to form our products. Okay, so let's look then at how we can affect the number of collisions. So if we want a reaction to take place faster or change how quickly the reaction takes place, we just simply need to change the number of collisions. And one of the ways we're going to change the number of collisions is changing the concentration of a solution, or indeed the pressure of a gas. Okay, so what is concentration? Well, concentration is to do with the number of particles you have in a given volume. So if we had, say, our reactant A, and what we're going to do then, we've got a low concentration of B. So you can see here we've got a very low concentration of particle B, not many particles per unit volume. A slightly high concentration of particle B, so there's more particles per unit volume, and a really high, much higher, well, not much higher concentration, a high concentration of B, and now a really high concentration of B. And hopefully you get the idea here that there's more particles to collide, and therefore you're going to get a faster rate reaction. Now, we've got to talk about exam speak. When we talk about there's more particles to collide, we can't just say that. We need to say there's more particles per unit volume. Now, what I mean by per unit volume, you could say per centimetre cubed, you could say per litre, per decimetre cubed, or you can just say per unit volume. So in the exam, I would say the effect of concentration is a high concentration leads to a faster rate of reaction because there are more particles per unit volume, and that results in more collisions per second. Again, it's really important that you say per second and not just saying more collisions. Okay, so another factor that can affect rate then is temperature. And again, it's literally because that with changing temperature, we're going to change the number of collisions. And hopefully you know that the reason that we're going to change the number of collisions is because that we're changing the energy of the particles. Wait a second. So we're changing the number of collisions between particles. Particles are actually moving faster at higher temperatures and slower at lower temperatures. Okay. So higher temperature, particles have more kinetic energy, the particles are moving faster, and then results in more collisions per second. Okay, so I've got a little example here just to show you. If we look here, we've got a reactant A, and we've got our particle B, just one particle of B, and this is a low temperature. You can see our particle just moving along slowly, and it's colliding, giving that a number with particle A. Okay, obviously at higher temperature, the particle has more kinetic energy. So now our particle is going to be moving much faster. There's going to be more collisions per second, and hence a faster rate of reaction. Now, okay, if you're doing a high paper, you may want to bring in another thing to do with temperature. Not only do we get more collisions per second, okay, because we get more collisions per second, that will lead to a faster rate. But we also need to consider whether those collisions are what we call successful or unsuccessful. So what's a successful collision? Well, in a successful collision, your particles collide with enough energy for them to break apart, as we show in here. Okay, so they need to break apart and then reform our product. Now, we can also have what's called an unsuccessful collision, and this is where particles don't collide with enough energy for them to actually break apart, and all they simply do is bounce off each other. Okay, so they haven't collided with quite enough energy. Obviously, at a higher temperature, your particles are moving faster. It's much more likely that one of these collisions between particles will be successful. And there's a term we use in chemistry to talk about this minimum amount of energy that the collision must release, and it's called the activation energy. So in a successful collision, there's enough energy there, the proportion of collisions that are successful is going to increase at higher temperature. More particles meet the activation energy for the reaction. And then we're going to look at surface area. So surface area, you need to understand first of all what surface area is. Well, basically surface area are the particles that are on the surface of an object, okay? And what I've got here is I want to imagine, I mean, this is a 2D representation. I want to think of it as like a cube, all right? And I've cut the cube in half. Basically, the only particles that this particle here could react with are the particles on the surface of the cube. Once you imagine these particles within the middle, the particle can't reach, okay? So we work in a 2D world here. Now, the way to increase the surface area of a solid, and by the way, it's always a solid with surface area, you can't increase the surface area of a liquid. So increase the surface area of a solid, all we have to do is we have to chop the particle up. Okay, now if we look here, we can see here, there can only be collisions at the surface of reactant B. Okay, but what I can do, if I want to increase my surface area so we can react with these particles, we just chop our object up. Okay, so I'm going to break my object up. And by doing so, now I can expose those particles in the middle. It's a bit like an apple. If you think about an apple, the skin of the apple is the surface, but we cut our apple in half, we then expose the flesh on the inside, and we could cut it into quarters, expose more flesh, cut it again and again and again and again until we get more and more of the surface exposed. Thing to point out here then is that the smaller you make an object, the greater its surface area. Well, you've got to bear in mind, I always think about if I've got, let's say, 10 grams of apple, and then I cut it up into smaller and smaller pieces, I've still got 10 grams of apple, but a lot more surface. Okay, so higher surface area, more collisions per second, because there's more particles at the surface to react with. And I've just got a little picture here. This is a picture of a custard powder factory. And the thing about custard powder, as the solid form, when you get it out of the tin, it's not very flammable. But if you create a dust from that powder, so you're spreading the powder out, you increase its surface area massively, and then it burns so quickly it actually explodes. So you have to be very careful with substances that could potentially set on fire. As a big bulk substance won't set on fire, but if you increase their surface area, you can form an explosive mixture with air because you get such a much faster rate of reaction. Okay, and then the other factor we need to consider is what's called a catalyst. So catalysts are substances that speed up chemical reactions, okay, without undergoing any chemical change themselves. So they're very, very important and very, very useful things. So because they don't get used, undergo a chemical change themselves, they don't get used up in a chemical reaction, and this means we can use them over and over and over again. So how do catalysts speed up reactions? Well, this would only be for a high tier candidate, really, to explain the role of catalysts. I mean, everyone needs to know what a catalyst does, chemicals that speed up chemical reactions without undergoing a chemical change themselves. If you're doing higher, though, you need to explain why. And the reason is that they don't actually, like temperature and concentration and surface area, result in more collisions per second. But what they do lead to is more successful collisions per second. So you'll still get the same number of collisions per second, but more of them will actually be successful. And the way they do this is that they lower the activation energy of the reaction. So, for example, we've got a reaction here. This is a reaction of hydrogen peroxide. And hydrogen peroxide breaks down naturally to form water and oxygen. It's a very slow reaction at room temperature. Okay, so you'd maybe notice a few bubbles on the side of the glass. But if you add your catalyst, and see here the catalyst for this reaction is a substance called manganese oxide, the reaction is incredibly fast then. And what the manganese oxide has done is it's lowered the activation energy for this reaction. So that collisions that were before were unsuccessful because there wasn't enough energy in those particles. With a catalyst lowering the activation energy, those particles then may collide with enough energy where they will actually have a successful collision. So catalysts, they don't increase the number of collisions per second, but what they do is they lower the activation energy, so there's a greater chance of a collision being successful. So you could say a catalyst increases the number of successful collisions per second by lowering the activation energy. Okay. Really important catalysts, as I said before, we find them in car exhausts. The reason we have them in a car exhaust is that they speed up the reaction of harmful gases coming out the engine into less harmful gases leaving the car via the exhaust. Obviously, there's not much time for these gases to be made less harmful. So we have a catalyst in the exhaust that speeds up the process, the chemical reaction, by which these harmful gases become less harmful. Thing about the car exhaust, these catalysts, they have a massive surface area because, as we said before, the bigger the surface area, the faster reactions are. So they have a big surface area. And the catalyst is renewable. So, well, not renewable, it doesn't get changed in the chemical reaction. It's just simply its presence there makes it faster. And what that means is that the exhaust could theoretically last the lifetime of the car. So, yeah. Interestingly, in these exhausts, the catalyst is a metal called platinum, highly valuable metal, which is why lots of car exhausts are now being stolen, or the catalytic converter on the car exhaust is. They're not just useful in cars, though. They're very useful in industry, and it's worthwhile knowing why. And the main one is really, it's, well, 1 and 4, okay? They save energy. So it's obviously in industry, you want to make your product as quickly as possible, as fast as possible, so you can sell more stuff. The one way of doing that is by using a high temperature. As we said, higher temperature, you're going to get a faster rate. But using a higher temperature costs money. So what you can do is you can use a catalyst, and the catalyst will lower the temperature at which you can make the reaction go fast enough. So rather than using a high temperature and costing money, put a catalyst in and you'll get a much faster rate of reaction at a lower temperature. So very, very useful. And of course, that's also good for the environment. If we're not having to use energy for reactions to occur fast at the speed we want, then we're not using energy, we're not burning fossil fuels, and we're not releasing greenhouse gases. Okay, so that brings us on now onto how we actually study rate of reaction. So to study rate of reaction, really we need to look at the balanced equation. I'm just going to go through this here. So we've got here a reaction. This is between magnesium and hydrochloric acid. And you should be familiar with these state symbols. This is the symbol S for solid. This is the symbol for AQ for solution. Here you can see that the product magnesium chloride is in solution. But the interesting thing here is that we're producing hydrogen, which is a gas. Now, as I showed on the first slide, we could actually collect that gas, that hydrogen gas. Okay, there's the gas being formed, and we can see how quickly that gas is forming. And to do that, we'd use two pieces of equipment. One piece we could use is what's called a gas syringe. Okay, so here's our gas syringe. So as the gas is forming, we collect the gas in the gas syringe and we record that over time. We can record every minute how much gas is being formed or what volume of gas is being formed. So it's well worth remembering this name of the equipment, the gas syringe. If you don't have a gas syringe, there's another technique we can use, and this is where we use a measuring cylinder full of water. And we collect the gas with a delivery tube, and as the gas collects in the measuring cylinder, it pushes the water out, and we can record the volume of gas being formed. Now, there's another technique we can use with a gas being formed in a reaction. So when you're being asked about how you can monitor rate, just look at the equation. If you can see a gas, collect the gas using a gas syringe or using a measuring cylinder full of water. There is another technique we could use, and before I talk about that technique, actually, I'll talk about the gas, the graph we get. So here's the graph we get with collecting a gas. And you can see at the start, we've got no gas, but as time proceeds, we collect more and more gas. The interesting thing about this graph you get, though, is that it starts to curve off, okay? And we get a less steep curve. So it's steep, and it gets less steep, and then eventually it becomes flat. Why is that important? Well, this is where we need to talk about graphs. So the steeper this curve, the faster your reactions go in. You know, you're collecting more gas in a short amount of time. But as it gets less steep, okay, here, this is showing us the reaction slowing down. We're still making gas every minute, but it's just less and less gas with every minute. And eventually we get to this point where effectively the reaction is almost over now. There's been very little gas formed over these couple of minutes here, and that's telling us the reaction is slowing down. And eventually we get to this point here where we see it goes flat, and that means the reaction has actually finished. Okay, so that's an important slide there for you. Just to point out, the reaction's fastest at the start because this is where we got the highest concentration of reactants. As you know, high concentration, more particles per unit volume, more collisions per second. As time proceeds, though, reactants get used up, the concentration of them drops, there's less collisions per second, and so a slower rate. Okay, so we'll just move on very quickly then. So these are the key points in this kind of curve. The steeper the curve, the faster the reaction. Over time, reactions slow down, they become less steep, and eventually, where they go flat, we know the reaction's finished. So, for example, in this reaction, we could estimate the time that it's finished is at this many minutes. Now, yeah, this brings me on to the other method where your reaction forms a gas. We can also weigh the reaction. What we should see is that as we weigh the reaction, it actually decreases in mass because we're losing particles from the reaction. So what we'd do is we'd place our reaction onto these set scales and we'd record the mass of the reaction and we'd see the mass dropping as the gas is forming. Okay, and here's a suggested table of results. You can see here there's a big drop in the amount of gas given off in the first minute, and with each subsequent minute we're still losing mass, so we're producing gas, but the amount of gas being lost is getting less and less with each passing minute. Okay, so you can see here I've worked out how much gas is being produced. This is the start mass, this is the mass after 1 minute, after 2 minutes. So we're just subtracting to see how much gas has actually formed. And again, we get a similar graph as the volume of gas graph. Obviously, a different axis on there, though. Now we're looking at the mass of lost from the reaction. And I'm just going to point one thing out here, by the way. We said we'd do this with perhaps this reaction between magnesium and acid. The problem with that is the gas we're producing is hydrogen, and you could not measure the loss in mass if the gas was hydrogen, because hydrogen is a very low density gas, so the drop in mass is very, very small. If it was hydrogen gas, you would have to use a gas syringe or a measuring cylinder full of water. But this technique here, where we weigh it, could be done with carbon dioxide, because carbon dioxide is actually quite a dense, heavy gas. So you would actually be able to record the loss in mass. You could also draw your graph like this, where you don't bother to work out how much gas has been formed. You could just literally, look at the mass of the reaction and see that it drops. Again, you can see there's a big drop at the start, but it gets less steep, meaning we're losing less and less. The loss in mass is getting less and less, and it goes flat as we'd expect. So it's the same graph, just upside down. Okay. So let's look at a typical rate graph, rate versus time graph question. So we've got 5 grams of magnesium added to an excess hydrochloric acid. We're collecting the gas for 10 minutes in a gas syringe, and we plot the graph. Okay, so we get this graph here. So one thing they might ask you is, well, how long does it take for the reaction to finish? So all you have to do here is find the flat section of the graph. Okay, and you can then work out the amount of time, and I'm estimating here between 6 and 7 minutes for the reaction to finish. Okay, and it's asking us to produce a line that we might get at a higher temperature. So hopefully at a higher temperature, reactions go faster, and therefore we'd expect to see a steeper curve. So we'd expect to see a curve like that. Okay, so we can see reactions going much faster. One thing I want to point out, we would expect the amount of gas to be formed to be exactly the same, because all we've done is change temperature. We're not changing the amount of reactants. We're not going to make more gas. We're just going to make that gas quicker. If you drew a graph like this, you may get a mark in the exam because you're still showing the reactions going faster, but this is showing that you're producing more gas, and you wouldn't be able to produce more gas, you just make it quicker. The only way you could get that line there is that if you increase the mass of the magnesium used, okay, because if you're using more magnesium, then you'd make more gas. So yeah, just to point out as well, that blue line, this line, we could also use that for doing a higher concentration, because that would have a faster rate of reaction. Or we could have also, if we increase the surface area of the magnesium, so instead of using a solid piece of magnesium, perhaps we used a powder form of the magnesium, which has a great surface area. Okay, now there's another reaction that I'm going to show you. This time, we could perhaps collect the gas here, this sulfur dioxide gas. There's a problem though, this sulfur dioxide gas is very soluble in water, so actually you wouldn't actually collect any gas. But there is something else about this reaction. I'm just pointing out here as well, you don't need to learn this equation. It might be worthwhile practicing balancing it, putting the big numbers in. But yeah, state symbols. So we mentioned earlier that AQ means a solution, and solutions are clear by nature. Now, if we look on the right-hand side, we can see that the sulfur has a different state symbol. It's got the state symbol S, which stands for solid. Okay, now a solid forming from 2 solutions mixed together would actually it's called a precipitation reaction, because it forms a precipitate. That's what the solid is. And that precipitate causes reactions to go cloudy. Okay, and if you look here, we can see a reaction that's been left. This is a reaction, the fire sulfate reaction, and we can see that cloudiness over time. So we start with clear, and over time it becomes cloudy. This is that sulfur precipitate forming, and we can use that sulfur precipitate forming to actually monitor the rate of reaction. So one way we can use this sulfur precipitate forming is using a light sensor. So we pass light through our reaction. At the bottom of our reaction, we have a light sensor, and that light sensor would actually detect that less and less light is passing through the reaction due to that sulfur precipitate forming. Okay, so we get a graph then that looks like this. At the start of the reaction, our reaction's clear, lots of light can pass through it to our light sensor, so we have a high light intensity. But as time proceeds, we form precipitate. That precipitate stops light passing through our sample, and therefore the light intensity drops. Again, we produce a curve like this. We can see here there's a big change in the light intensity, so the sulfur precipitate's forming quickly, but it's forming less quickly as we go here. It's becoming less steep. And at this point, we can see no more sulfur precipitates forming until our light intensity stays the same. What did it look like at a high temperature, high concentration, or with a catalyst? Well, you know that the reate's going to be faster, and so therefore we'd form our precipitate much faster, and so we get a steeper curve. Okay, so anything that looks like that. Okay, now with a precipitate form, there's another method we can use, and it's where we place a cross underneath the reaction. So I've got an example here where I'll show you. Here's a reaction. We've got the thiosulfate reaction over the cross. I've had to use white just to, you to envisage that the reaction's clear so you can see the cross below. Now, let's say we start the reaction. As we say, it's clear, so we can see the cross, it's quite visible. But as the precipitate forms, precipitate starts to form, and that precipitate stops the cross from being visible. And so we could actually then monitor the rate by seeing how quickly it takes for that cross to disappear. Okay. The less time it takes for the cross to disappear, the faster the reaction. So we could plot a graph like looks like this. We've got the temp. Let's say we want to see the effect of temperature and rate of reaction. So we plot temperature versus the time it takes for the cross to disappear. And well, I'm going to let you think about what that graph might look like. I'll give you a second or two to think about what the graph might look like. So as we increase temperature, time it takes for the cross to disappear gets less, and so it should look like this. Okay, at a low temperature, it's taking a lot of time for the cross to disappear. At a high temperature, it's taking much less time for the cross to disappear. We'll plot a line of best fit through these points. That looks like this. Okay, practice your lines of best fit. They're very important for exam papers. Okay, and then what we're going to do there is we're just going to move on and talk about the variables that we can control in this reaction. So anything that affects rate is going to be crucial to control if we wanted to monitor one of these. So if I wanted to look at temperature, I would control all these factors, keep them the same. If I wanted to look at the effect of concentration, all these factors would be kept the same. We only change one variable at a time. Okay. In this experiment, though, we'd also have to make sure that the depth of our solution was constant. So we'd have to use the same equipment in this reaction, because what we wouldn't want is to have perhaps a wide beaker where the solution's quite shallow, and therefore, the cross be quite visible, even quite a lot of precipitate forming, and then use a much narrower beaker where the same volume of solution would be much deeper, and so the cross would disappear much faster. So there's quite a lot to control in this experiment in terms of the control variables. Obviously, the things that would affect rate would have to be controlled, but also the depth of the solution that you're going to have in your reaction. Now, obviously, you do have the same volume, so that won't be an issue, but you've got to make sure you're using the same kind of shape, size container for the reaction to take place in. Okay. Which method's best? Well, the method I would use here would be the data logger. Why? Because judging when a cross disappears involves judgment. Okay, and a data logger, the only problem with a data logger is expensive, but the data logger gives much better results. So yeah, data logger is definitely a better method because it doesn't involve someone judging the cross is still there or the cross isn't there. However, data logs are expensive and they're quite hard to set up. So typically you're going to be using the cross method if you do that in school. So that's the end of the session, and I hope you found it useful. And yeah, thanks for sticking through to the end.